Okay, so our last section we're going to look at in chapter 7 is 7.6. We've done this kind of thing before where we solve trig equations, but we did it graphically. So when you do it graphically, you might draw a picture and you might find where two graphs intersect, or you might find where they cross the x-axis. Graphing is great, especially when you get equations that are really hard to solve algebraically, like cubic or even higher degree equations. Because we don't really have algebraic formulas for solving cubic equations. They exist, but we don't know them. We have a formula for quadratics, so that's mainly what we're going to focus on when we do this algebraically. I can't give you anything harder than a quadratic if I want you to use algebra, which is what that means analytically. So some of the techniques that we're going to use, I mentioned factoring. What's the other technique I mentioned for solving quadratics besides factoring?
Quadratic formula.
Yep, you can always use the quadratic formula. Even when you can factor, you can use quadratic formula. It's going to take longer. So I suggest if you can factor to do that. And you have to write everything in terms of one trig function. When you have a quadratic equation, you would not have something like this. That is not really a quadratic equation that you can use the quadratic formula on. The reason is you have two different variables. Okay, so what we have to do is get everything with just one type of thing in the problem. Okay? Either all x's, or in our case, it's going to be all the same trig function. All sines, all cosines. Okay, you can't do it with different trig functions. And generally, the strategy is if you see something that's squared, like this one, you're going to try to replace that. That's the thing you want to get rid of. You're going to leave sine alone. You're just going to replace cosine squared. Also, I'm only asking you for the solutions between 0 and 2 pi. That means you don't have to put plus the period times n. I know there's infinitely many solutions to a trig equation, but I'm not asking you for infinitely many. Just between 0 and 360, okay, or 0 and 2 pi. All right, so here's our first equation. Kind of looks like it could be a quadratic because you've got something squared, and then something, and then just a constant. But the problem is two different trig functions. Okay, we can't work with that. So we're going to replace the thing that's squared, and I'm giving you a hint at a trig identity that will help you do that. If I rearrange that Pythagorean identity for cosine squared, can somebody tell me what cosine squared would equal if it was by itself on the left of that equation? Yeah?
1 minus sine squared.
Right. You move the sine squared to the other side by subtracting. So cosine squared is 1 minus sine squared. So fill that in right there. Change what's in that box to 1 minus sine squared. Keep everything else the same. It's important that once you do that, you leave it in parentheses because we're doubling everything that was in that box. So 1 minus sine squared is now in the box. The whole thing is doubled. Plus sine x plus 1 equals 0. All right, so what I'm going to do now is I'm going to distribute the 2, and I'm going to write this in descending order. Highest exponent to lowest. Actually, you know what? Let's just distribute the 2 first. Don't worry about writing it in descending order yet. So I've got 2 times 1, but then I've got a plus 1 at the end. So 2 times 1 plus 1 will give me plus 3. So I'm going to put, and I said don't worry about descending order yet. So I'll just put plus 3. You don't have to put the plus in front. So positive 3. I'm going to have a negative 2 sine squared x, and then plus sine x. Okay, so now we've got kind of a quadratic equation. It's not really written in the standard order, and there's something wrong with the number in front of the squared term. If you want to attempt to factor something, we always like that to be what kind of number? I'll give you a hint. It's not what it is right now. Yep? Positive. Positive. You always want the squared term to be positive. So what I can do is just move everything to the other side. So basically change the sign of everything. So 0 equals, and now as we move it, put it in descending order. So 2 sine squared x. So we added it. We're going to subtract the sine x, and we're going to subtract the 3. Now we've got a quadratic type equation in the right order. So the problem you're basically trying to solve right now, if I just kind of write this below it, you don't have to write this if you don't want to. I'm going to put that in quotes because that's basically the problem you're trying to solve. 2 times something squared minus something minus 3. If you can factor what's in quotes, you can factor what's up above it. It's going to factor exactly the same way. Okay, so sometimes what I do for people that have a hard time with it is I factor what's in black first using x, and then I change all the x's to what they really are, sine x's. But let's just see if we can factor what's in red right away. So we're going to have 2 sets of parentheses. And what would be my first term in each set of parentheses? I'd have to have a what and a what?
A 2 and a 1.
Can you be more specific?
Positive 2, positive 1.
Not quite, because if I multiply that together, it wouldn't give me 2 sine squared x.
No, 2x and 1x.
Okay, you're more on the right track. That would be for the black one. It would be 2x and 1x.
2 sine x and 1 sine x.
Yes. So we'd have 2 sine x and sine x. Good. X. Now, from here, we just have to follow the rules we normally do. 2 numbers that multiply to give us 3. And the signs, well, it's a negative 3. So that means you have to have one of each. 1 positive, 1 negative. So let's try a 1 and a 3. And should I do negative positive or positive negative? Yeah? All right, let's give it a try and see what happens. So you get 2 sine squared, we already got that. 2 times negative 1 gives me the negative 2. 3 times sine gives me a plus 3. So that gives me negative 2 plus 3. Is that what I wanted in the middle? Because remember, that's like a negative 1 sine x. So what do I have to do to fix that? Yep.
Put the negative in the first.
Yeah, just change the signs. Now we get 2 times 1, that gives me 2 sine x, minus 3 sine x. 2 minus 3, there's your negative 1. Okay, so now we've factored it. And once you factor it, what do you do with each factor, each thing in parentheses? Set it equal to 0. So now we've got 0 equals 2 sine x minus 3, and 0 equals sine x plus 1. So now the next step is to get this by itself in each equation. If this was a regular factoring problem, that would be the last step, because what's in the box wouldn't be a sine x. It would just be an x. Okay, so we have one extra step at the very end, which is to get rid of the sign. But first, get what's in the box by itself. So Jay, for the one on the left, what 2 steps would I have to do to get that by itself?
You would add the 3 to both sides and then divide by 2.
Yep, so add 3, divide by 2. And I'll do the other one at the same time. Minus 1. And now, how about Juliet? To get rid of sine, what do I have to do on both sides?
You take the sign of each side, or I don't know.
Yep.
Take the arc side.
Yeah, take the arc sine of each side or take the inverse sine. Either way. So take inverse sine. Take the inverse sine. Remember, I didn't do any multiplication in that step at all. That is taking and plugging everything into a function. So that cancels. And now I need the inverse sine of 3 over 2. Now, if you're clever, you should recognize something quick. So I'm going to remind you, when you graph sine, what's the highest and the lowest that it goes? 1 and negative 1. What's 3 divided by 2? 1.5, 1.5. Sine doesn't hit 1.5. If you're asking where does the graph hit 1.5, it never does. So I can already tell quickly by looking at that, and that's good because I don't have a calculator, that there's no solution. Okay? There's no solution to this part. Sometimes that happens, sometimes that doesn't. We're really going to need a calculator at some point. All right, so this part has no solution. If I try it on this calculator, just 1.5, and then try to do the inverse sine, it says invalid. You can't do it. All right, but the other one, does sine ever hit negative 1? Definitely. It does hit it, so that part has a solution. How do you find it? Do the same thing we did on the other side. So inverse sine, regular sine cancels. And now this is one that luckily, well, I don't need my calculator now, but I can just think about where the graph hits negative 1. So in my head, I just kind of quickly picture this and ask myself, where is that point? It's the 3/4 mark of the cycle. So where is the x value of that point? Remember Sam?
3 pi over 2.
Yep, it's 3 pi over 2. It's 0, pi over 2, pi, 3 pi over 2, 2 pi. If you didn't know that, what you could do is, if they wanted the answer in radians, I would not do it in radians. Because if you do that, watch what you get. If you do second inverse sine of negative 1, you're going to get 4.71, negative 1.57. Hold on 1 second. So 3 pi over 2, if you look at that, that's 4.71. But we got negative 1.5. Oh, it's the same answer. Okay, so what we have on the board is correct because the directions said to give answers between 0 and 2 pi. Technically, negative 1.57 is the same answer. It's going the other way. And that's the one the calculator is going to give you. So actually using the calculator kind of messed me up here, but we did it right. Either way, though, my point was, if you do it in radians, you're going to get that crazy decimal. Okay? You're not going to recognize what it is as a nice answer. So what I always do is, if they want the answer in degrees, I do it in, or they want the answer in radians, do it in degrees first. Now I got a nice answer, negative 90. And then if they wanted it between 0 and 360, I would just say, all right, just add 360. And now I get 270, which is 3 pi over 2. How would I figure that out? I could just convert 270 degrees to radians by hand. Right? So that's how I always do it if they want it in radians. Do it in degrees first, and then convert it manually to radians, and you'll get a nice fraction, not a decimal. Okay? Calculator, it just can't give you those nice fractions. It's going to give you 4.71. Okay, any questions on that one? Okay, so that's probably one of the easier ones because first of all, it did factor. You didn't need quadratic equation. Half the problem you didn't even have to do because you got no solution. So you only really had to deal with 1/2 of it. Okay? And that 1/2 only had one answer. I didn't have to think about the ASTC diagram because 3 pi over 2 is not in a quadrant. If you get a point that's on an axis, you're done. You don't have to worry about this ASTC thing. It's when you get a point that's not on an axis, then we got to start thinking about all that stuff. Okay? In the 180 minus, 180 plus, but not here. All right, let's try this one. So what's the first thing that's wrong with this that you have to fix? Yeah.
Make it all equal to 0.
Okay, we got to get it all equal to 0, and I'm going to put everything on the right. And if you're thinking, well, wait, why would you do that? Don't you want the squared term to be positive? Yes, and that's why I'm going to put it on the right for now, because you'll see what happens in a second. So I'm going to put 0 equals negative 2 sine squared. The 1 was already there, and the cosine was already there. Just kind of getting it ready to be in descending order. Okay, what do I have to do next? Yeah?
Get the first term positive, so change.
Not yet. Something we have to do before that. And it's automatically going to do what you just said. And that's the reason I put this on the right-hand side. Even though you might be looking at it and be like, well, wait, it's negative. Wait 1 second. Yep.
You kind of have to put it in terms of cosine, right?
We have to put everything in terms of cosine. So we're going to replace that. What is sine squared equal to using this identity? Oh, Sam?
1 minus cosine squared.
Wait, sine squared is 1 minus cosine squared. So I'm going to replace what's in the box with 1 minus cosine squared. And now I'm going to distribute that negative 2, and the squared term is automatically going to be positive. That's why I did it that way. If you don't think of that beforehand, that's fine. You're just going to have to move stuff around until you get it to be positive. So you're going to have 0 equals 2 cosine squared x. And then I'm going to have negative 2 plus 1. So negative 2 plus 1 gives me a negative 1. And then plus cosine x, that just stays the same. Now we're ready to factor it or use quadratic formula. All right. Let's see if we can factor that. Okay, because we have a prime number at the end, there's not many options to multiply to get 1. So if it doesn't work, you're going to know pretty quick. It's not like that number is a 12, where you might have to try 4 and 3, 6 and 2, 12 and 1. There's not that many options here. So we would have a 2 cosine and a cosine. Has to be a 1 and a 1. And the signs have to be... What do my signs have to be? Yeah?
Plus and minus.
Has to be a plus and a minus. And you only have 2 options. Try plus and minus, try minus and plus. If neither one of those work, go to quadratic formula. Let's try plus minus. And that's going to give me 2 cosine times 1 is 2 cosine minus cosine. 2 minus 1 gives me 1. So this does factor. Okay. Right, now we're going to set each factor equal to 0. But what I'm going to do is I'm going to kind of solve it as I go. So with the first factor, I would add the 1 and then do what with the 2? Divide it. So I'm going to add the 1, I'm going to divide by 2. And now that one's ready. And the other one, cosine x plus 1 equals 0. I would just subtract the 1 to the other side. Now that one's ready. Well, cosine x equals negative 1. We just did that, I think. Oh no, we did sine x equals negative 1. All right, so we'll do cosine x equals negative 1. All right, I'm going to do the one on the right first because anytime you have a sine or cosine equal to a 1 or negative 1, the answer is on an axis. There's only one answer, and I don't have to think about ASTC stuff. All right, so in my head, I'm going to look at cosine. There's all my quarter points. I'm looking for the quarter point that's the second one. brings me halfway through the cycle. So what's the x value for that second quarter point? Yep. Pi. If you didn't know that, you could type it in on the calculator. Remember, it might give you a negative answer, and if they don't want that, you're going to have to add 360. So if you can visualize it in your head, you can avoid all that having to add 360 and the calculator messing you up. So x is pi, or I'll do it in degrees, 180. And now for the other one, what am I going to do on each side? Yep.
Multiply by r cosine.
Can you say that again?
Take r cosine.
Right. Think of, when you write this, think of this with a big box. You have to take a bunch of stuff and put it in that box, and think of it as the inverse cosine box. Right? You're going to put a bunch of stuff in the inverse cosine box, and you're going to get some answer out. But it's not multiplying. So we're going to plug that number into the inverse cosine, and then we're going to plug all of that into the inverse cosine. That's going to cancel. And I get that as one of my answers. So let's type it in. Second inverse cosine of a half. Get a nice answer in degrees. That doesn't always happen, but we did this time. So x equals 60 degrees. Or what's 60 degrees in radians? Keeping in mind that 180 is pi. Yeah. Pi over 3. 60 is 1/3 of 180, so 1/3 of pi. Now, is 60 degrees on an axis? No, it's in a quadrant. So now we need to think about where else is cosine equal to a positive. Because remember, this said cosine x equals positive 1/2. We just got an answer here. What other quadrant are you going to get an answer in? Yep. 4. And the formula to get an answer in quadrant 4 is 360 minus your reference angle. Our reference angle is 60. So the other answer is 300. Or, if you want to quickly convert to radians, 60 times what is 300? 5. So just multiply by 5. And there's your other answer. And if you're not sure you did it right, take the cosine of 300. If you take the cosine of 300, what we just solved for, you should get 1/2. So let's check. Cosine of 300 gives you half. So that is the other answer. And you could check cosine of 60, but that one shouldn't have been messed up, because that one we typed in directly on the calculator. Okay, so your three answers here are 60, 180, and 300. Or pi over 3, pi, 5 pi over 3. Okay, any questions on that one? Okay, that one's a little bit harder than the first one. Not quite the hardest one we're going to look at, but it is a little harder, okay, because it has more answers. All right, so this is just a reminder. I just want you to read this before you write it down, because I'm reminding you that there are infinite solutions, but that is not what we're doing today. I just don't want you to forget that technically those three answers we just found in the last problem, they reoccur every period, every cycle. But we're not focusing on that today. But you need to remember it. So don't worry about putting plus a period times n on any answer today. Okay, let's look at this one. Again, directions are consistent with what I just told you. We're only finding the answers between 0 and 2 pi. Okay, so this one's it looks a little tricky because you don't have something squared. right? And I said to you, usually you're going to end up replacing the thing that's squared. And we know we're trying to work with quadratics, so if there's not something squared, how are we going to factor or use quadratic formula? So eventually you will. You will have something squared. Does anyone have a thought about which trig function I'm going to try to replace? There's really only one that you can replace, because the other one is already simple. It's one of the basic ones, and you can't really do anything with it. Does anyone have a thought which one we're going to try to replace? Yeah?
We'll replace tangent.
We're going to replace tangent. Okay, sine and cosine are the two most basic ones. You can't really change sine and cosine into anything. So, how can I rewrite tangent? Yeah? Let's start with that. Sine x over cosine x. And now, what could I do from there? Because we don't want to have fractions, but there's something I could do to both sides to get rid of the fractions. And we kind of did this in the homework. Yeah?
If you multiply it by cosine.
Yeah, multiply everything by the LCD, which in this case, there's only one denominator. So multiply everything by cosine. And Jane, what will that give me on the left?
3 cosine squared.
Okay, so on the right,
Yeah.
you're going to get 3 cosine squared. How about on the left?
And then just sine.
Just sine. Now you're good to go. Okay, now you're at the point where I basically started you off with this problem. This one's actually, let's see, now it's going to be about the same length. I don't think this one's going to factor. So let's go through it and see what happens. Now out of sine and cosine squared, which trig function am I going to replace? Yep. We're going to replace cosine squared. And can you tell me what we're going to replace it with?
1 minus sine squared.
Yep, 1 minus sine squared. So now I'm going to distribute and then get everything on one side so the squared term is positive. So sine x equals 3 minus 3 sine squared. And now let's figure out how we can get sine squared positive. What do I have to do to make that positive? And doing this and one other thing will also help me to get 0 on one side. Yeah, John?
Add 3 sine squared to both sides.
Yeah, we're going to add the 3 sine squared, and then what about the 3?
Subtract.
We're going to subtract it. So we're going to end up with 3 sine squared x plus sine x minus 3 equals 0. Now we've got a quadratic equation, but I don't think that that one is factorable. You can try, but yeah, I'm almost positive it doesn't factor. So I'm going to use quadratic formula. Just like you would on a basic quadratic, let's identify what A, B, and C are. Okay, Dylan, what's A?
3 sine squared x.
Remember, A, B, and C are just
3.
the numbers. So yeah, A is 3. How about B?
1.
1, and C?
-3.
-3. And even though it's a quadratic equation with trig functions in it, we're going to solve it just like we would if there were no trig functions. All right, so now let's do the quadratic equation just like you normally would. Okay, but remember, when you solve with quadratic equation, say you have this. When you solve, what are you solving for when you solve this equation? Yep.
X.
You're solving for x. Look where x is in that problem. It's right here. That's the thing you're solving for. So now, when we do this one, we're solving for the thing that's right there. You're not solving for x, you're solving for sine x. So once you use quadratic formula, you put those answers and set them equal to sine x. Don't set them equal to x because they're not x. Okay, so let's go through it and see what happens. So So we get negative b plus or minus b squared 4ac all over 2a. Just double check my signs as I go in case I make a mistake. I think we're good. Okay, minus, I'm going to change that right now. And 4 times 3 times 3 is going to give me how much?
36.
Plus 1? 37 over 6. Okay. So now, if I was solving this, I would just put equals x. But now I'm going to put, what did I say to put? Equals sine x. So at this point, what we're probably going to want to do is break this out into 2 separate problems. Instead of writing it with a plus and minus, I'm just going to write it twice. So negative 1 plus root 37 over 6, and negative 1 minus root 37 over 6. And now solve each one. And remember, each answer can have up to 2 using the ASTC diagram. So we might get 4 answers out of this. Let's see what happens. Let's start with the one on the left. At this point, I'm going to change that to a decimal. And I'm just going to do it to 3 decimal places, so that's accurate enough. So we've got negative 1 plus the square root of 37. Negative 1. Negative 1. A little difficulty. Negative 1 plus square root of 37. So I'm just going to do that first. I'm going to divide by 6. And now I have 0.847. Now, what do I have to do on both sides to get the x by itself? Yeah.
Take the other side.
Take the inverse sine. So x equals inverse sine of 0.847. 0.847. So I get an answer of 57.87 degrees. But remember, sine is also positive in what other quadrant? Yep, it's positive in 2. I just got an answer in quadrant 1, 57. What do I do to get the answer in quadrant 2?
180 minus 57.
Yeah, 180 minus the answer I just got. So 122.11. And technically I shouldn't put equals, I should put approximately equals, because these are not exact answers. Okay, so there's our 2 answers from the left part. Now let's do the right part. Negative 1 minus the square root of 37 divided by 6. Okay, I already see a problem here. So I'm going to write that down and then see if anyone can tell me what's going on. Negative 1.180. Okay. Any thoughts about what I just wrote down there? Yeah?
It's greater than, or it's less than negative 1. So.
Yeah, it's less, yeah, technically to the left of it on a number line, so it's less than negative 1, so we can't do it. If you try to type that in, you're going to get no solution. It doesn't mean the whole problem has no solution. It just means I don't get an answer from that part of the problem. The other 2 answers are correct. Okay, in your book, when they did it out, they did it in decimal radians. So they had 1.01 and 2.13. Okay, any questions on that one? So, not really harder than the last problem, but different because now you can't factor. You get to use quadratic formula. That one's pretty much the same. I don't really think there's anything new to learn from that problem. All right, let's try this one. It asks me to find all solutions in one period. And I'm even giving you a hint that the period is between negative pi over 2 and pi over 2. The period of this problem is 180 degrees, or pi radians. Okay, so first thing I like to do is get everything with the same trig function. What has been the trig function that we've replaced all along? Which one do we always try to replace? Yep.
Tangent.
We don't always replace tangent. There's another rule I said to go by. Always replace the one that's what? Yep.
More complicated.
We've talked about that, but not today. We haven't been necessarily replacing what's more complicated, but we've been replacing the term that is. Look back at this one. Well, actually, which term would you replace in this one if we did it? Yeah?
Cosine.
Can you be more specific?
Cosine squared.
Mm-hmm. Cosine squared. Which term did we replace in this one at that step right there? Okay.
Cosine squared.
Cosine squared. How about in that one? Which one did we replace? Yeah.
Sine squared.
Sine squared. So what's common to everything we just said? We've always replaced the one that was
Has an exponent, or in the case of the one we're about to do, the one with the higher exponent.
close. The one that's squared. We've always been replacing the one that's squared. In the problems we've done, yes, it has been the higher exponent, but I don't want you to think of it that way. Just think of replace the one that's squared. That's what you want to do. And that's the same thing you're going to do here. Replace the one that's squared. I'm not saying you couldn't do it with replacing the one that's to the fourth power, but we don't have any identities that have things to the fourth power in them. Okay? We do have identities for things that are squared. And does anyone remember the identity for that has secant squared in it, and luckily it also has tangent in it, so it's going to work perfect. Yep.
1 plus tangent squared.
1 plus tangent squared equals
Secant squared.
secant squared. It's already arranged the way we need it. Replace secant squared with 1 plus tangent squared. Leave tangent to the fourth x alone. And do I need parentheses around what's in the box? What do you think? Not really, because there's nothing I'm distributing. That 1 plus, that's not a distributive property. So you can just change everything that's in the box without parentheses. All set?
Yeah.
Okay. So 1 plus tangents. I'm going to write it this way so it's more clear. So there's the 1 from up above. There's the other 1 from my identity plus tangent squared. Okay. Any questions on that? Now, what I'm going to do is get everything on one side, and I want to have the highest term. You always want to be positive when you're going to try to factor. So I'm going to leave that where it is. I'm going to subtract tangent squared, and then I'm going to subtract 2. Now, when you look at that at first, you might be like, well, wait, that's not a quadratic, because the highest exponent isn't 2. But it is a quadratic type of pattern. You can use the quadratic formula on that, or you can factor it if that works too. Anytime that this exponent is double that exponent, and the last number is a constant, and those two bases are the same, tangent, tangent, it's definitely a quadratic pattern. Anything that looks like this, we'll call that to the 2x plus something to the x plus a constant equals 0. You could put anything you want in those boxes, and it would be a quadratic equation. Okay? As long as this exponent is double that. All right, so now let's see if that factors. Yes, I think that will factor. So we're going to start with 2 sets of parentheses. Now, what would I put for my first term? What would I put in the first parenthesis, and what would I put in the second? Yeah?
3 tangent squared and tangent squared.
Yep. You'd put if this was just an x, you'd put like 3x squared and x squared. We're going to put 3 tangent squared and tangent squared. Now, my constant is a negative, which means I'm going to need a positive negative. I'm going to try it that way. And I need 2 numbers that multiply to give me 2. 1, 2. Let's check. So now we've got 3 tangent to the 4th. We've got 3 times negative 1. It's negative 3. 2 times 1 is 2. Negative 3 plus 2, negative 1. Perfect. That's how it factors. And now what do I do with, Leo, what do I do with each factor?
Set them equal to 0.
Set them equal to 0. What would you have to do with the first factor to make that happen?
You have to factor out the 3. No.
Nope, you're just going to get this by itself.
Alright. Subtract 2 over 3.
Yeah, subtract the 2 and then divide by the 3. And that would equal tan squared x. Now, you can't do inverse tangent yet because you still have the square. So what would I do on both sides to get rid of squaring? Yeah? I would take the square root of both sides. Square root and square cancel. So now on the right, you have tangent x. So now normally the next step would be to do inverse tangent on each side. But what's going to happen here? As I said, normally you do inverse tangent. You're not going to here. How come? Yep. Yep, Jane?
Number will be imaginary.
The answer would be imaginary. If you take the square root of negative 2/3, that's going to be imaginary. So we're not even going to deal with that. So from that part of the problem, we don't get any answer. So now we're going to look at the other part. So if I set that equal to 0 and get tangent squared by itself, Trevor, what would tangent squared equal?
Tangent squared tangent.
Well, what number would be on the other side?
Oh,
1. Yep. So we get tangent squared equals 1. Now we can take the square root of both sides. Square root, square root. And tangent x would equal, what's the square root of 1? Or negative 1. There's 2 answers. So tangent x equals positive or negative 1. If you want to split that into 2 problems, so now it's kind of splitting into 2 problems again, all right? And it did when we factored, now it's splitting again. So tan x equals 1, tan x equals negative 1. And now we're going to do inverse tangent on both sides. So inverse tangent of 1 and inverse tangent of negative 1. Does anybody remember what angle you take the tangent of and you get 1 as the answer? It's in the isosceles triangle with opposite and adjacent are the same. It's a 45. So if you know that, you can make this problem very quick. X is 45, and think of the other quadrant where tangent is positive, quadrant 3. 45 plus 180 is how much? Yep. 225. And now if you want to get the other one, if you're not sure about negative 1, it's going to be a negative 45. But if you didn't know that, you could just type it in. So you get negative 45, but be careful, because they said, oh, no, that's fine. They said to give answers if you're thinking in degrees, negative 90 to 90. So I'll come back to that and just make sure all our answers fit that criteria. So x is negative 45, and the other answer would be, let's see, a 45 degree, that's my reference angle, and I am negative in this quadrant and this quadrant. Negative 45 degrees, which quadrant is that? 2 or 4? About Sam? No, not 2. Negative 45 is when you go clockwise 45 degrees. Okay, so that's quadrant 4. So we just got the answer there. How would I get an answer in quadrant 2? 180 minus 45. But look at what the directions said. It said to only give answers between negative 90 and 90. So even though technically those answers are all correct, the only answers they want me to write are those two. So in this problem, technically you did not have to worry about the other answers. And if you recognize that beforehand, which I didn't, you wouldn't have even had to think about the ASTC thing. It wouldn't have mattered. Any questions on that one? Okay, we haven't done a factor by grouping, and then I think we'll probably finish up with one of those. All right, so factor by grouping usually means you've got 4 terms. 1, 2, 3. That's 3, 4. Terms are separated by plus and minus signs. For factor by grouping to work, the first 2 terms have to have something in common, and so do the last 2. Abby, what do the first 2 terms have in common?
They both have cosine in them.
Both have a cosine, so let's factor that out. So I get 2 cotangent minus 3. Now the goal with factor by grouping is when I factor out whatever the last 2 have in common, I need to end up with 2 cotangent minus 3. This has to appear again in the problem to make factor by grouping work. Okay, so let's look at the last 2 terms. 6 cotangent x minus 9. What do those both have in common?
Yep.
A 3. So I'm going to factor out positive 3. 3 times 2 gives me 6 cotangent x. 3 times negative 3 gives me negative 9. Perfect. So now, what do these both have in common? This term and this term, they both have 2 cotangent x minus 3. So now, pull that out. Yeah, let's do it like this. So that's going to be on the outside. If I take that away from the first term, I'm left with a cosine. If I take that away from the second term, all I'm left with is a plus 3 equals 0. Now, Tessa, what am I going to do with each of those factors? Yeah, we're going to set them equal to 0. Let's do the one on the right first. Cosine x equals negative 3. Thoughts before I go any further on that one? Yeah?
Cosine doesn't go down to negative 3.
Cosine doesn't go to negative 3. There's no solution from that part. So if you try the inverse cosine on each side, it's not going to work. So don't waste your time. Let's look at the other part. Cotangent x equals, add the 3 and divide by 2. So now, to get rid of cotangent, normally you would have to use inverse cotangent. We don't have a button for that. But if you were going to type cotangent into the calculator, how do you do it? What button do you use? Yeah?
The tangent button.
use the tangent button, but you do what with it?
Divide 1 divided by tangent.
And what does that do to it? When you take 1 divided by something, all you're doing is really taking your fraction and you're flipping it. So instead of thinking that as cotangent of x equals 3/2, think of it as tangent of x equals 2/3. Flip it. When you flip cotangent, you get tangent. When you flip 3/2, you get 2/3. So all I did was flip each side because now I have a button on the calculator and I can do inverse tangent. So that's a little trick that can come up if you ever run into secant, cosecant, or cotangent. Flip it, and then you can do inverse with the button you have on the calculator. Okay, so now let's see what we got. So second inverse tangent of 2/3. The first answer should be between 0 and 90, and it is. So that's the quadrant 1 answer, 33.69. And what other quadrant is tangent equal to a positive in? Yep. 3. So now I'm thinking 180 plus 33.69. 213.69. Now I'm going to go back up and check and see if they said to only give answers between something and something. If they did, maybe I can cross one of those answers off. So it says find all solutions in one period. So in that case, we can leave both answers. Okay, because when I quickly look at that, I know the period of that is 2 pi, because it can't be smaller than 2 pi. It can't be, because cosine has a period of 2 pi. Okay, so any questions on that one? Okay, so the book, they put 0.59 and 3.73. That's what those would be in radians, if you want to check. All right, those two are pretty much the same, and that one's kind of the same. So let's do one with a double angle. Do you want to do 5, number 18, or 6? 5 and 6 are pretty much the same thing. Almost identical. That's a little different. So actually, let's either do 5 or 18. Any preference on which one? No, Gracie, I'll let you pick.
5.
5. They're really almost the same thing. They're not very different at all. So let's do 5. Okay. Do we have all the same trig function here? Yes, we have all signs, but something else is wrong. What's wrong here that we can't really do this? Yeah.
The 2 has to be on the other side.
Yeah, we can't have arguments that have an x and arguments that have a 2x. Everything has to be a sine x. So we're going to replace this. Does anybody remember what you can replace sine 2x with? This is one of our double angle identities from yesterday, and you only have one choice. Yep.
Minus cosine squared.
Remember, it's not squared.
Oh.
So you want to look for your double angle identity.
Sorry, I was looking at the wrong.
You were thinking of the Pythagorean one.
Yeah.
Gracie?
Is it 2 sine x cosine?
Yes. 2 sine x cosine x. Okay. Now I'm going to get it equal to 0, just like we always do. So 2 sine cosine minus sine equals 0. And now what could I do on the left-hand side there? Yep.
Factor out a sine.
Yeah, let's factor out a sine. And we're left with 2 cosine x minus 1 in parentheses. And now we're at the last step. Set each factor equal to 0 and solve. So let's start with sine x equals 0. So you're asking yourself, what is the inverse sine of 0? Think of the graph of sine and where it hits 0. Here and here. And I'm just going to go back up and look at what they want for answers. Between 0 and 2 pi. So they want both of them. So what would be the x values of those two coordinates? Yeah?
0 and pi.
Yeah, 0 and pi. So 0, pi. Or if you wanted to do degrees, 0 and 180. Okay, just kind of practicing both. And now we're going to set the other one equal to 0. So Tanya, can you tell me what cosine x would equal when I move all the numbers to the other side?
1/2.
Yep, cosine x would equal 1/2. And that one I think we already did earlier, if I can find it. Somewhere. Yeah, right here. Cosine x equals 1/2. So we got 60 and 300. So I'm not going to go through it all again, but just look back at number 15 if you want to see how to do it. So 60 and 300. So x equals. And in radians, that was pi over 3 and 5 pi over 3. Generally, in fact, on the test, I'm not going to ask you for both degrees and radians in the same problem. I'm going to ask for one or the other. So if you were giving the answers, it's fine if you just say 0, 180, 60, 300. You don't have to put them in order lowest to highest. I don't care about that.
Well, that was what I was going to ask. It had to be like in order.
No, if you have all the answers, that's fine. If you were going to solve number 18, you would pretty much do the exact same thing. Almost identical problem. Example 6, that's a little different, but it's nothing you haven't dealt with before. So if there's one like that in the homework and you want to look at it, we can tomorrow. All right. So problems 1 through 10 are easier than everything we did in class. Okay. In fact, the only ones that are as hard as what we did in class are 16, 19, and 14. Everything else, they start you off. Okay? Like problem number 7 is this. Sine x minus 0.5, cosine x plus 0.3. They factored it for you. So they're starting you at the step where all the factoring has been done, and now you just have to go from here. Okay? Up till like number 12 or 13, they start you off. And then the last 3 problems, you got to do everything on your own, just like we did in class. Okay? So 1 through 14, 16, 19. We'll look at that tomorrow. And this will finish up chapter 7, and then the last 2 sections of the week are much easier than what we did yesterday and today.